Please settle down. All right. May I start now? All right. Thank you for being here. I'm Matteo Simone, and this talk is almost a sequel of my previous one about frog computing. This is about frog checking. So we will talk about frogs yet again, but we will use them in another way. We will talk about frogs in another way. So we will start by doing a quick recap on frogs. What are frogs? Why are frogs? Why are we talking about frogs? Then we will talk about Prism, because we will use Prism to model check our frog model that we will build on our third part. So, frogs yet again, but just a little bit, not the whole talk like last time. Last time we talked about frogs, frog rules. So what are frogs? How do frogs behave? MPP systems. So a nice way to model frogs and dynamical systems. And we spoke about agent-based frog simulations. So almost what they have done with Uta Stansburiana, but with frogs, not in Godot engine, but with NetLogo. That doesn't crashes when it has hundreds of lizards. It just keeps on. So, frogs. What are frogs? We don't care about what frogs are, sadly. We just care about those two frogs and the secret third frog. So we have Pelophylax lessone and Pelophylax ridibundus. They are nice frogs. This one is smaller, this one is bigger. This one lives everywhere in Europe, but in Russia, I think. This is bigger and lives everywhere in Europe but Spain. Set for Spain. They can mate between them. Although they are two different species, they can mate, and they produce a beautiful hybrid that is Pelophylax esculentus, which has all the intermediate characteristics of the original species. So its size is in the middle. The vocal sacs are basically gray. These ones are darker. Those are white. It has all the middle ground characteristics of the original frogs. A nice way to model an LE complex, Lessone esculentus complex, is via a minimal probabilistic P system. This all basically just boils down to a set of individuals and a set of rules which model the behavior of our systems. These rules of the MPP systems are basically composed of some kind of individuals that we need to apply the rule, that are consumed by the rule, a set of individuals that are produced by the rules, a promoter, which is something we need to even take the rule in consideration, and some rate f, which is the probability or the rate at which these rules is applied. So these all just looks garbled, but we don't actually need to know the details. I don't even know them myself, so it's fine. These are the rules for our systems, our LE complex, our MPP systems. So we have these rules that rules reproduction. So we have a kind of frog, a female frog, a kind of male frog, with X and Y being the species of the female and male frogs. These are consumed, but they are spawned right back, so they are not consumed actually, to produce a juvenile frog Z. We don't believe in tadpoles. They are just juvenile frogs. And this is the rate of the reproduction, which basically just means take the sexual preferences of a female frog towards the species of the male one, take into account the number of males and females of those species, and take into considerations how many kinds the species pairing can produce. So either one, if those species can produce only male or female juveniles, or two, if they can produce both male and females. This repr means that we must be into one of the 3 reproduction stages we have. One simulation here is made up of 4 stages that alternate between reproduction 1, 2, and 3, and a selection stage, which basically mean frogs either die, grow, or just survive. These are the rules that command this selection stage, which basically mean we have a rate of gx to survive, or 1 minus gx to die and return just empty. A juvenile in the selection stage can grow, so it loses the juvenile. And the rate function for the selection rules takes into account the selectivity of the environment, how much the environment is harsh, and the overpopulation of the environment with the fitness of the species. These just will be translated later in another form that we will use to do some model checking. So, to do this model checking, we will use Prism. Prism model checker is a model checker. It allows a construction of several kinds of models on which we will verify some properties written in an LTL, CTL style with probabilistic stuff. It allows to use its reward system to get some quantitative results on the properties. And it also has some nice stuff like plotting, simulations of the path the model can take, statistical experiments that we will need to do statistical model checking, and so on. Prism models are basically made of modules. We will later have just one module, so some stuff we won't need it. Each module has its own set of variables, so its own state, its own behavior. Behaviors are modeled via commands. Modules can synchronize between them with some actions, and we can set up a reward system, as I already said, that allows us to get some quantitative results. Prism allows several kinds of models. These 3 are the most common ones, so discrete time Markov chains, continuous time Markov chains, Markov decision process. Basically, with DTMCs, behaviors or commands have probabilities, while in continuous time Markov chains, behaviors have rates. So the average time we expect to pass between an application of the command and the other one. And non-deterministic models, we will only care about discrete time Markov chains. Commands are the way modules do stuff. They're written as an action that we need to synchronize modules. We won't care about actions. They have a Boolean guard, which is based on the state of the module. Then we have several updates, either one or more updates. Each update has its own probability or rate if we're in a continuous time Markov chain. We can have one or more update. Each update can update more than one variables. I mean, they're written like this. We don't really care about this since we're just doing a bird's eye view of Prism and its application for statistical model checking. If more than one guard inside a module is verified at the same time, Prism just split the probability of picking them between all applicable rules. Unless we're in a non-deterministic model, in that case, we don't know the probabilities of picking them. Properties are the way we get some results from the models. Property either gets us a true-false result, like in this case. This is asking Prism to tell us whether it's true or false that the probability is greater than 1 for, at some point in time, f future, eventually, the label stable is verified. So this kind of property gets us either true or false. This kind of property with equal question mark gets us a probability. This is asking what's the probability at the steady state S that Q is equal to some target Q max. So we can either get true or false or some probabilities usually, or rewards. Rewards are written like that. They also have a guard. So in this case, the reward power consumption is updated to get plus 0.13 if in this simulation step SP is equal to 0 and these other kinds of guards. They can also have actions to synchronize with the modules. So they are quantities. Rewards are quantities that we increase over time. We also have reward-based properties. So if we want to verify properties on rewards, we have the operator R. We can, if we have more than one reward, we can pick one of them to be analyzed with the brackets and all that stuff. This property is asking what is the reward power consumption accumulated, C, up to time t. This one is nastier. It has filter states. We don't really need those. Lucky us is asking what's the minimum reward in time steps for the path that eventually satisfies the label it in all the states, filter states that verify this property here. So we can compose, we can make some nasty properties and verify them thanks to Prism. Properties are written as an operator, bound prop. Operator is P for probability, S for steady state probability, and R for reward operators. So can be R min, R max, P min, P max. The min and max operator are used in non-deterministic models because we cannot have one specific answers for non-deterministic models, so we can only ask for the maximum minimum of that property. Bound is either this one to get us a numeric value, or comparison operator to get true or false results. The prop part is the main one. It is either a logical formula or a linear time logic style. So we have these operators that are the most common one. We basically only use F and U. So F means that the property is in some point in time verified later. We don't care how much in the future, at some point. Always the box operator, diamond box operator, if you're into that kind of things. The always operator means that the property must be verified at all points in time, at the next step, and we don't need weak until. We just care about until, which has an like A until B means that either B is true or A is true until B is. So it kind of makes sense. We will need until to make Prism happy later, so we don't really need to understand those stuff right now. We can combine them and ask if what's the maximum probability of eventually having always the label hungry one to be true. So we can combine operators and make some nice formulas LTL style. Okay, so that's all we need for Prism. Now we will take the model we had our previous time in frog computing and make it into a Prism model to do some frog checking. So in the original paper, there was the nice MPP system that I've used to make the Prism model. Also, thanks to Professor Milazzo, there also were the translation rules to turn an MPP system into a Prism model. The part that we care about are the rules that I've shown earlier. Those rules have been translated into Prism commands. So this is the boring stuff. We have just a single module which has 3 sets of variables, all describing almost the same stuff. So all these sets describe the number of frogs, where L means lessona, F female, M male, esculentus, and so on. J means juvenile. So we have one set that describes the total number of individuals we have. One set for it's just a working set that we take frogs off and then put later on, and a set describing new frogs that are being created either via reproduction or growth when a juvenile gets old. All variables have bounds, so they can, in this case, they have a lower bound of 0 and an arbitrary max amount of value. We can see that we are replicating informations 3 times. They can have an arbitrary upper bound, and the state of the module is the product of all possible values these sets can hold. So we can easily imagine that the possible number of states explodes really fast, even with some lower upper bound on the variables. Since we have this problem, we cannot ask Prism to build the model and make some normal probabilistic model checking, because Prism just says, sorry, I've run out of memory, I must die. So we cannot ask Prism to build the model. We have to turn to statistical model checking. That means we won't look at the whole behaviors, at the whole possible behaviors of our model. We will ask Prism to run like 1,000 simulations, 1,000 paths the model can take, and then gives us some statistical results on those 1,000 of runs. So these are, oh my god, it's shit. These are rule rewriting rules. So these were included in the paper of Professor Milazzo and Barbuti. It looks rough, really rough. I wasn't understanding how to translate the MPP system into a Prism model, because I really didn't want to read and understand these rules. Once I've read them and understood them, it was piece easy. So this just is saying, take all the condition, the OR of all the conditions for all your rules as a guard. So if one condition, if one rule can be applied, we will proceed to the update stuff. If no conditions, if no rules can be applied, then we just do this other rule. And the updates are in the form of probability and update, with probability being the probability, the rate of the rule we're trying to apply, if it is applicable, over the sum of all the probabilities of all other applicable rules. It's a mouthful. It's also a lookful. It looks messy. It will look messier in the next slide, where I'm showing the actual translation of reproduction rules. This other rule is applied when no other rule can be applied. This is just the synchronization step of the MPP algorithm to apply rules. So we consume all we can consume, then we apply all the updates on our sets, and then we go on. So this is the monster that we get from translating only the selection rules. This is horrible. I hated it. No, I actually liked it, but it's horrible. And I have to shrink it down to fit in this slide, so it looks even nastier. This means the OR of all the condition for all our rules. Then we have like, can we apply the rule LLX, meaning female lessona, male lessona that produce a female juvenile? If we can, then we take this probability of applying the update over the total rate. If we do apply it, then we take one lessona female from the working set, one lessona male from the working set, and we, if we can, if we're not over the upper bound of our LMJ new set, we put one juvenile in that set, and so on for all the rules. So this is basically just really take all the conditions, look for what rules you can apply, take them with the probability of that condition over the sum. I won't show the survival rules because that is even more massive, because we have one rule for each kind of frog, where the kind is either Lessona or Esculentus, male or female, adult or juvenile. So we have 6 different variables to mesh, and then we have one rule for the survival and one rule for the death for each kind. So you don't want to see it, really. You really don't want. It's even nastier than the one before. So each simulation year is divided in 3 reproductive stages, 1 selection stage. During the reproductive stage, all female try to mate. They do mate. And during the selection stage, each frog tries to survive, which with the rate we have shown before. If they do not survive, they die and they get taken off the total set. If they're juvenile, they do not just survive, but they do grow old and get into the adult set. At each simulation step, we pick one rule like we have seen before, so we take the probability of that rule to be applied over the total rate. If we can, then we take off the consumed frog from the rules. We take off the frogs that were used from the working set, either add frogs, modify the other set, if they die, they make juveniles, and so on. When no more rules can be applied, we go to the next stage by synchronizing the set, so the juvenile set, the new set is added to the total set, and then the working set is just refreshed to be the total frog set. We have seen the reproduction rules. We have one rule for each male-female coupling with the species. And we have an additional rule if both male and female juveniles can be generated, because not all pairings can produce male and female. Some rules can produce only female frogs, for example. But this was shown in frog computing, so you all already know this stuff. When a rule is picked, we remove the parents from the working set, we add the juvenile to the set of new frogs. And for the selection rules, we just have more rules, because we have one for each kind of individual, one for survival, one for dying. When a rule is picked, we remove the individuals again, and we modify all of the other set to work out the numbers. We can't use normal probabilistic model checking because of the size of the model. The number of states is ridiculous, so Prism just runs out of memory and tough luck. So we recur to statistical model checking, which runs usually 1,000 is the normal value of simulation. So it generates thousands of random paths, and then it computes some statistical stuff to get us a result given a confidence interval. We don't care, I don't even know what it is. Almost joking. And we have just 2 experiments. Our first experiment is an ideal frog world without sexual preferences. You should already know what could go wrong in a world where frogs do not have sexual preferences, meaning that female frogs do not prefer one species over the other. What could go wrong, you should already know. To check this, we ask, what's the probability, so P equal that, what's the probability of having 0 male or 0 females, which is the step just right before extinction, which is the probability of having this stuff in T years. We need the until operator, so years minus equal T until m tot equals 0 or f tot equals 0, because otherwise Prism just starts crying and saying, no, this rule is not true in some paths, I cannot give you anything, please retry again. So we cut short unnecessary long paths. We do not care if we're checking whether this is true for 10 years. We do not care if the simulation goes on over 10 years. We just cut that path and say, yeah, no, it doesn't go extinct in 10 years, trust me. So we can see from this property that in 50 years the probability is roughly 1. So they go extinct in roughly 50 years, while in 30 years they are at 0.9 probability of extinction, so it does not bode well. So what if we implement sexual preferences like they do have in nature? So we model the true Lesson Esculentus complex. In reality, Esculentus males are shunned. They are not really well liked from female frogs, while female frogs have a strong preferences towards Lessona males. They are the Chad, and they are the other kind of, don't know, the beta, don't know. I'm not into that stuff. Since the population doesn't go extinct, we cannot use a property like the previous one. We have to do some other stuff to ask nicely to Prism to compute us some numbers. So we had actually to take a reward consisting in all the frogs being born and a reward consisting of all the frogs dying, and we have to compute those two separately and then just take the difference, and this is the result. So in 30 years we previously had a probability of extinction of 0.9. Now we have more than 2,000 frogs, starting with 200 or 100, I don't remember. So this is not going extinct at all. So this is nice. This checks out with the paper, with our previous experiments we've made in frog computing, so we are all happy. And this was possible with the trick of the rewards, because Prism doesn't allow us to make a property that subtracts one reward from the other. We cannot have negative rewards. It really is just picky sometimes, so we have to do some other stuff to trick Prism into being happy, like ourselves, I guess. So we took a maximally parallel P system, we translated into a Prism DTMC model with the rewriting rules provided by the paper of Professor Barbuti and Milazzo. I have spent an asinine amount of time in working out that the until operator was needed to cut short the paths. I was just cutting short with like 50,000 steps, but Prism wasn't happy at all, so it just kept on crashing after hours of simulations. So the until operator is the trick to cut short unnecessary long paths. In the paper and also in frog computing, we've made some other kind of experiments, but we don't really need them now. We're doing other stuff. We're just taking a look at Prism to model and do statistical model checking that is required to get some results from an impossibly huge model state-wise, of course. And we also needed the reward system to trick Prism into saying how many frogs living, dying there are. So this was really short and sweet. Thank you for the attention.